So we'll get started on our I'll start with a brief review of last time's lecture. So last time we had started talking about a new topic, and that was related to mixing of granular materials. And we just did a very small amount of an introduction to this. So I'll do an introduction and then I'll just briefly review some equipment for mixing. So we saw, that mixing is important in many industries, and because almost all products are blends of powders. All the solid powders, they are not just one single element, but there are many different components mixed together. Whether it's pharmaceuticals, detergents, food, cement, fertilizer, and so forth. And really, this mixing is different from fluid mixing, mainly because particles flow in a different way. And what you find is that the mixer geometries and designs are different. And I'll show these to you in a little while. And one of the other things that's important is that generally the power consumption is much higher because these flows are so dissipative. We also saw that one way that we can try and see how well things are mixed is to calculate something called the standard deviation. So supposing we take n samples from various points in the system, and we find that xi is the sample, is the concentration of, let's say, the ith sample, where this xi could be either number fraction or volume fraction of whatever species you're trying to mix. Then if you have this set of numbers xi going from 1 to n, then the mean concentration is just given by this. And then the standard deviation is given by this number. And we also saw last time that if you have a completely segregated system, then the standard deviation is just given by x bar into 1 minus x bar. And I mentioned that typically if you plot, let's say, the intensity of segregation, which is defined as S divided by S0, then you start with 1.0, and then, usually it will go, and then for fully mixed system, let's say, it might go to even 0. But what we find, and I'll show you why, but it usually plateaus to some number that is, sorry, so if we define the intensity of segregation as S by S0, then your intensity of segregation will start at 1.0 if a system starts at time t equal to 0 in the completely segregated state. Then it will start at 1, that is S must be equal to S0. And then, with time, what we find is that actually it goes to some value, I'll call it as S infinity. And I will tell you what that is in a little while. But there may be some cases where, it actually goes down and then it actually increases. And this may be due to segregation, and we'll study that also in one of the classes that will follow. So the black line shows mixing up to some final state, and the red line shows a system in which there's first mixing and then it's followed by segregation. Let me next tell you a little bit about the types of mixers. I'll just show you a few mixers that are used, which are commonly used. So if you look at one very commonly used mixer, it's called a ribbon blender. And this is a photograph of this. So you can see that the cross section is like this. So it's like a top part is like rectangular and the bottom part is cylindrical. And then you have impellers inside which will rotate, and the material is put inside and then it gets mixed. And if you look at these impellers, this is what it looks like. So they are essentially ribbons. So there's one ribbon which sort of scrapes the side walls, and then there's an internal ribbon, and these are all helical ribbons, and they push the material in opposite directions. So the material moves in opposite directions when you're looking at the axis direction. And the rotation creates quite rapid mixing in the transverse direction. So you don't have any stagnant regions in here because the ribbon is constantly. Instead of having this type of a ribbon, sometimes you have a same sort of geometry, but instead you may have paddles like this, which will go through and mix the material. So this is showing a numerical simulation of a paddle mixer. And you can see how the red and blue particles are being mixed. A second type of equipment that is used is what is known as an internal screw mixer. So here, this is one axis, and so this screw rotates like this around in this conical container, and also there is another screw, so this also rotates about its axis. So what it does is it constantly pulls the material upward and then deposits there, and then it goes around. So you get a pattern that is formed where the material is pulled up and then deposited. So it's much lower energy than the helical ribbon mixer, but and so it's also much less intensity, and more gentle mixing takes place in this. So if you have fragile particles and you're not worried about how fast you want to mix, then this is a good mixer. And then these are all sort of tumbling mixers, or you can say they're just rotational. So you get various kinds of shapes, and then they are mixed by rotating about an axis like this. So the particles fill only part of it, and then as it rotates, some flow is created and mixing also. But you can see that as the thing rotates, there's a greater area of flow and then there's smaller area of flow. So there's converging, diverging type of flows occur, and so there's good mixing because of that. And here also it's a similar thing that you have V blender. So there are two cylindrical tubes that are joined together, and then it rotates here. So all the particles fall down here, and then when it rotates, then they all get divided between the two cylinders. So there's this constant shuffling motion, and that creates good mixing. And of course, the simplest tumbling mixer is the rotating cylinder. So this is often called a drum mixer, where it just rotates around its axis. So these are all the different kinds of mixers. And here we have a high shear mixer. So sometimes you have sticky particles, or particles that don't flow very easily. Then you can have, say for example, cohesive materials. then you can have high shear, high energy mixing. It's very rapid, but of course, a lot of energy. And the reason for the conical shape is that, when you rotate things, there's a centrifugal force that's generated, and because this is at an angle, that pushes the particle upwards. So there's a natural movement upwards because of the centrifugal force, and then it comes down. And then since these impellers are rotating fast, they will break any agglomerates that form, and the tip speed could be as much as 30 meters a second. So very, very fast rotating things. So this just gives some idea about the different kinds of mixers. Of course, in these kinds of equipment, there is always a huge number of designs. I just gave you a very small sampling of the designs that are available. A very large number of such designs are available. So now let's go back to the notes, and I'll introduce some more material. So today we are already on the 25th of October. Semester is coming to a close. So there are essentially 5 more lectures left. And, I had missed one lecture. So actually there are at the most 6 more lectures. Today is the 25th of October. And we are on lecture 34. So if you remember, last time we were talking about all of this. And one of the things I mentioned is that if you have perfect mixing, then S infinity is 0. And this is correct. But what usually happens is that if I want to discuss what is the final mix state.
Sir.
Yeah.
Screen is not visible.
Uh-huh. Thank you. Okay. So we were talking about all these things last time, the mix state and so forth. And what I said is that the final mix state, the standard deviation will be 0. But this is actually not quite correct. And the reason for that is actually the accuracy of measurement. So if you want to look at, the final mixed state, okay, and then you look at measurement errors in that, then what it turns out is that if there are small n particles in the sample, in a sample that we have taken. So you remember we had taken n samples over here, and we had measured the concentration to be xi. So now, if there are n particles in a sample, then, there is a measurement limit. So you can either have, because of the error, you'll have plus minus 1, let's say, particle. So then the closest that you can get to a particular concentration is, let's say, 1 by n. You can't have half a particle. It's only one particle. So then, you can just say that the least count is 1 by n, because it has to be at the most you can. So if you have 5 particles, your concentration can be either 0.2, 0.4, 0.6, 0.8 or 1, 0, 0.2, 0.4, 0.6, 0.8 or 1. So, there's a least count of 0.2, that is 1 by n if there are 5 particles. If there are 100 particles, then your least count will be 0.01. So like this, there will be a least count, so you can't really go more accurate than this. So if this is the case, then in this case, you can show that the lowest value of your standard deviation at long times, even in the limit of perfect mixing, this is going to be equal to just x bar into 1 minus x bar divided by n. So this is actually the limiting value depending on how many particles you have started with. Now, sometimes you may start with, if a sample has 1,000 particles, then of course this number will become very, very small. If it has more particles, then you will be more accurate, but if you have less particles, then you will be less accurate. So what this implies is that S infinity is equal to 0 only if n tends to infinity. So only if you have a very, very large number of particles, then you will have S equal to 0. And if you just do a simple example calculation, supposing you are given that x bar is equal to 0.5 and n is equal to 100, then this gives us S infinity is just equal to 0.05. Okay. And your S0 is going to be equal to 0.5. So this is what it is, that you can essentially get only a 10-fold decrease in S. So in this particular case, even if you go to perfect mixing, so you plot S divided by S0, S infinity, S divided by S0 versus time, you start at 1 and then this will go down, and this lowest value will be 0.1 because it's S infinity by S0 is equal to okay. So this is what you will get. So this is something to be worried about and to keep in mind when you're doing any experiment, that there will always be some amount of error in your measurement, and that error will tell you, you may get an error in the mix state. So even though you're getting your S by S0 at long times to be 0.1, you may think, oh, I should do some more mixing. No, there's no need to go further because, as far as your measurement is concerned, this is the limit. You can't go lower than this, even if the thing is perfectly mixed. So then, supposing you want to describe the mixing, you can say that this is like a black box approach. We are not bothered about how the mixing is taking place, but only at a given time we are taking samples and then saying, okay, things are mixed or not mixed. But supposing you want to model the mixing, how do particles mix? Then we can essentially, so given a concentration So first, what I want to sort of say that assumption here is that particles are very similar. So there is no segregation. And I'm going to talk about what is segregation in a little while. That means particles don't separate out while they're mixing. And let's say the flow patterns are not affected by concentration of the species. Okay, so these are the two things that we'll assume. So that means it's as if you are mixing identical particles, but they're only of different colors. Then in this case, the mixing is determined by two factors. One is convection, that is the flow, and two is diffusion, that is due to the random motion of the particles. And here, the governing equation is given by del C by del T plus V dot gradient of C is just equal to D into del squared of C. Over here, V, so first of all, of course, C is the concentration. This could be the volume fraction or the number fraction or whatever you want to call it. This you decide. V is the velocity field, which is known, and D is the diffusivity. And for many systems, we can get D is just equal to some constant C1 into D squared by gamma dot, where D squared into gamma dot, where D is of course the particle diameter and gamma dot is the shear rate. So this is, so if you have a particular problem solve in which the things are very, very similar, then, you can. So we can think of a simple example problem to do, and that is, axial mixing in a drum mixer. So what this is there is a cylinder that is horizontal like this. We have seen these type of things before, and let's say only part of it is filled with particles, and this is rotating about its axis. So here we have no flow, and we want to know, let's say this direction is Z along the axis. So no flow there is no flow And what you want to know is what will be the mixing in the Z direction. So you can clearly see that here we have essentially, since there is no flow, then if you look at this equation, what you will see is that, let's say, for example, the concentration is higher in the middle and lower in the sides, then your C will be essentially determined. I mean, the variation of the concentration with time will be only due to diffusion because the velocity is zero. So in this case, the governing equation becomes just del C by del T is equal to d into del squared C by del Z squared. So this is nothing but Fick's second law, which you would have seen in mass transfer and all these things. And essentially you can get something like this. And this equation you can solve, and there are many ways of solving it. You can do a combination of variable solution. If your cylinder is very, very long, then you can do combination of variable solution. If you have a finite cylinder, then you'll have a sine cosine type of solution. So let's suppose that your cylinder is of finite size. Then let's say your C is given by some function of time into A. Before I write down the solution, I should write a little bit more about the boundary conditions. So since there can be no flux of material at the ends of the cylinder, and let's suppose this cylinder length is L, so then the boundary conditions are that del C by del Z, that is the flux of material at the, must be equal to 0 at Z equal to 0 and at Z equal to L. Okay. Now let's look at the solution. And here what we assume that the solution is something like C is equal to some function of time into A cos of omega Z plus B sine of omega Z. So from here, first of all, let's apply the boundary conditions to find out what is A and B, and that will make things a little bit simpler. So we get del C by del Z is just equal to F into minus A sine of omega Z plus, I'm sorry, so this is what del C by del Z is. I just want to say that this is an assumed thing because I know what the solution is. So for this boundary condition, so at Z equal to 0, so at Z equal to 0, what we get is del C by del Z is just equal to F into minus A omega. This is sine omega Z, cos and sine. I've just written it exactly the opposite. This should become sine, and this is cos. Okay, sorry. So this is the correct thing. So now if you see this at z equal to 0, you'll see the first term is 0. So you'll get this is just 0 plus b omega, and at z equal to 0, this is equal to 0. So this implies that b is equal to 0, because of course f cannot be just 0, so b is equal to 0. So then at z equal to L, we have again del C by del Z is equal to F into, now we know that B is equal to 0, so this is just this into minus A omega sine of omega L is equal to 0. So if for this to be satisfied, either A is equal to 0, which gives you the trivial solution, or sine of omega L is 0. If sine of omega L is 0, that means omega L is equal to n pi. So this gives us that omega into L is just equal to n times pi, where n could be 1, 2, 3, 4, 0, 1, 2, 3. This is 1, 2, 3. 0 is again a trivial solution. So in all of those cases, you will see that sine of omega L is 0. So now we have the complete solution. So this gives us that omega is equal to n pi divided by L. So now at least we know that our concentration is some function of time into a cos of n pi z by L. For now, each n will have a solution, and to find out what the n is, you need the initial condition. But we don't know what is f of t. So now that we can substitute into the governing equation. And since we know this, so then we can get df by dt into a cos of n pi z by L is equal to, is equal to d. And now if you take the thing twice, then you'll just get f into minus a n squared pi squared by L squared into cos of n pi z by L. So you can see from here directly that the cosine term cancels and a also cancels, and so you are left with df by dt is just equal to minus b into, I'm just going to call this as omega squared for the time being, knowing that omega is this, times f. So if you integrate this, then you'll get ln of f is just equal to minus d omega squared into t. This is if you integrate with respect to time. And so this means that f is just equal to exponential of minus. There could be a constant, but we already have one constant, which is a. And so we don't need that. So this finally gives us that the concentration C is just equal to, now we can write this as a series because we have large number of terms. For each value of n we will have a solution. So the solution is the sum of each term. So we can write this as just an cos of n pi z by l into exponential of, so this will give us the concentration profile. And we can get what is these constants an depending on what is the initial condition. So what did you start with? Where c is equal to some c0 of z. So if c0 of z is given, then you can easily find out what is n in this series. Let us start off with the simplest sort of case. Suppose C0, just for our own simple purpose, supposing C0 is just given by that we start with a, let's say, a cosine profile. Let's say C0 is just equal to cos of pi into z by l. So in this case, you will simply get the solution to be C is equal to, now a so n will only be 1, all the other terms will be 0, since your initial condition is this, so then at all times it will always remain like this. And then if you match the terms at t equal to 0, this first at t equal to 0, this term goes to 0. So you will essentially have an is equal to 1. A1 is equal to 1. And A2, 3, 4 all are 0. So instead of a series, you will get a solution which is something like cos of pi z divided by L into E minus D into pi squared divided by L squared into time. So this is the simple solution that you will get, and you will see that how as time proceeds, your concentration will finally become uniform everywhere. Okay. Maybe some little bit of thinking has to go into that, but so this is a very simple example that we did for actual mixing, but you can do many more complicated examples. And the reason I did this is because there are many experiments where people have actually measured this concentration profile, and we can actually find what is that this equation, or more properly, that this equation is shown to describe experimental results very well. So I will show you some of those results in the next class. Okay. Now let us move to another topic, and that is on segregation, because we cannot talk about mixing without talking about segregation. And here the basic point is that dissimilar particles spontaneously separate out during flow. And there are many examples of this segregation. So I'll not just talk about segregation in mixers, but in many systems. So for example, if you are, one of the earliest studies was, supposing you take a container and there are some large particles in there, and let's say for argument there's one large particle in there, and then you vibrate this, put it on a table which is just vibrating, or you can imagine that you've taken it on a truck and the truck is going on a rough road, so the container is being shaken up. Then what is seen is that the large particle rises. They rise. So this is something that is seen very widely, and this was among the first that was really widely studied, and it's called the Brazil nut effect. The reason it's called that is because Brazil nuts are actually large nuts, and if you have a container which has a mixture of different nuts, then the Brazil nuts, which are the largest, they are invariably on the top. So because whenever you're handling the container, it gets vibrated, and then so because of the vibration, the Brazil nuts come to the top. So this is why it's called the Brazil nut effect. And people have come out with the reasons why this happens. And one of the simple explanations is that during the upward motion, the particles below these large particles, the small particles come and jam in the space, and then when the particle tries to move down, because these particles are difficult to move out of the way, it can't come down. So it goes up because of the vibration, but then it can't come down. So like this, it just keeps rising. Another explanation is that there may be a sort of circulation pattern that is built up because of wall friction, and because of that the large particle goes to the top. So there are various explanations, and they are valid in different regimes of the operation. Another example that has been studied quite a lot is that supposing you have a quasi 2D system, that is, if you look at the side view, let's say there are two plates like this. And then you start pouring a mixture. Then obviously a heat forms. But what is found is that if there are two different colored particles, then you will form actually layers of the different materials. And so you get a layered structure. So you're pouring in a mixture of particles. They are well mixed initially, but when you pour them, then you actually end up forming layers of this. That first the blue particles, then the red, and so forth. So this is the and usually these are one of the particles is round and the other is angular. So this is driven by differences in angle of repose. So what happens is actually initially the round particles, let's say the red ones, they flow first and they go right to the end, and then they form a, then there are only blue particles left which flow later, and then the next time again red particles flow and then the other particles flow later and so forth. So you get this kind of layered structure. So this is, let's say this is one type of segregation that is been studied a lot. This is a second type of segregation, and but really the one that is very, very important is, let's say, segregation in flowing layers. And what here, let's say, for example, if you have particles flowing in a layer like this, so familiar Bagnall profile. So then what you find is, if you have segregation in flowing layers, you find particles with higher density sink in the layer. So that means they have a tendency to move down like this. And particles with larger size rise. So, this is for particles as the diameter is larger, they go up, and for those whose density is higher, they come down. So this is something that is been now widely accepted, and what you will find is that after some time, let's say if you're dealing with particles of two different densities, then if you plot the volume fraction of the heavier particles versus the height, then you will find a profile like this. That is, in the entire layer, there is no heavy particles present at the top. Then there is a mixed layer over here where there are both heavy and light particles, and at the base there are only heavy particles. So this is the concentration of the heavy particles. And similarly, if you made a plot of, let's say, the volume fraction of the large particles versus the height, then you will get essentially something like this, where you'll have a mixed zone somewhere in the middle, and then at the top you'll have only large particles, and then in the bottom zone you will have no large particles. So all the large particles will go up, and here, so you will have small particles at the bottom and large particles at the top, and then in the middle, of course, you have this mixed zone, whereas over here you have heavy particles at the bottom and light particles, light in terms of the density, heavy and light separately. So this is, so in the next class, what I'm going to do is I'll try and explain, can we actually predict how this segregation will take place? I will discuss a little bit about this. Okay. So we are slowly coming to the end of our course. There's maybe a few lectures. As I said, there are 5 lectures left. I may be able to complete whatever I wanted to teach maybe within the next 3 lectures or so. So maybe, so today is over, so maybe another couple more lectures I may take. And then what I'll do is I'll be available, and if you have any questions or doubts, both regarding the course or your project, we can have that. I was just thinking maybe we can have a short presentation on what is the progress on your project also in one of the lectures. So each group can make a 2 or 3 slide presentation to say what have they done so far in the project. Okay, so I'll let you know about that. Okay. So now I'll stop, and I'll see you tomorrow morning.